Hello, geometry students. I appreciate you finding time to get your notes taken care of. Today we're continuing on with our discussions of circles by looking at some additional lines that are going to interact with our circles, but we're going to take a closer look at this idea of things originating from a common endpoint. So please copy your title down, Lines in Circles with Common Endpoints, and also copy down your objective. Your objective for the day is the student will learn the properties associated with lines with common endpoints when they interact with circles. Okay, a lot of the ones that we're getting ready to look at, they are very similar rules, have very similar properties. Okay, the formula is just a little bit hard to understand. Okay, so hopefully you'll get it. As always, anytime you need more time to work on your notes, please press pause and then hit play when you're ready to move on. Okay. Now, as I said, there's many combinations of line segments that can interact with our circles. Okay, so if that's the case, then there are going to be many possibilities for different types of angles or different shapes of angles and different sizes of arcs that are going to be formed by these intersections. Okay, but fortunately, many of the situations that we're going to be seeing, at least today, are going to follow a single formula. Okay. Now the formula is written in a little bit of generic language so that it can be used and can adjust to different types of situations. Okay, the formula we're going to work with today is going to be like this. The measure of the angle, and that's the angle between the two guys or the two lines that are coming into the common endpoint, it will equal half of the difference of the two arcs that are caught between the two lines in question. Okay, so that formula is going to sound a little bit confusing at this point, but once you see it in action, I think you'll understand that it is pretty simple. One other thing to point out inside of that formula, of course, you see the two different arcs in there. One of them proclaims itself to be a large arc, and one of them is a small arc. Okay, that is basically because of the nature of these two lines coming from a common endpoint. Okay, when they come from a common endpoint and they move through a circle, as you are going to see, you're going to end up with one of the arcs, the one that's closest to the common endpoint, is going to be smaller than the one that is further away, simply because the lines have had a longer length of time to spread apart from each other. Okay, so large and small are the arcs that are bounded by the segments that are intersecting the circle. Okay. Now, this formula will change very slightly as we look at some specific uses of the formula. Okay, so let's take a look. The first situation we're going to look at is when two tangents originate from a common endpoint. Now, we've seen this situation somewhat already because we've talked about what the lengths of these two tangents should be doing, and hopefully you remember that the tangents themselves should be congruent. Okay. However, if we're talking about the angle measurement between the two tangents or the two arcs that are caught between the two tangents, that is where this new formula comes into play. And the rule said that the measure of the angle, which in this case is angle ABC, will equal 1/2 of the difference between the two arcs caught between the two tangents. Okay, so in this case we have a major arc, ADC, traveling around the far side of the circle, and then we have a minor arc, AC, traveling around the near side of the circle. Okay, so that's how this would apply for a typical two tangent type situation. Now, another situation that might arise is we may have, instead of two tangents coming from a common endpoint, perhaps this time we have a secant and a tangent coming from a common endpoint. Okay, so if that's the situation, then it might look something like this. We haven't had secants much. Okay, we'll get into them a little bit more here in the coming days. But again, looking at the angle and the arc relationship, well, the same rule still applies. The measure of the angle caught between the tangent and the secant, in this case would be angle EFG, that measurement will be 1/2 of the difference of the two arcs caught between the tangent and the secant. And in this case, we would have the bigger of the two arcs would be arc EH around the far side, and from that we would subtract arc EG around the near side. And there's one other specific that this rule will apply to, and that will be when two secants originate from a common endpoint. Okay, so two secants originating from a common endpoint and coming towards our circle might look something like that. And again, we'll look at the more information on the secants soon. Okay, but for now, we're still looking at the angle and the arcs relationships. Okay, and in this particular case, the rule still applies. The measure of the angle caught between the two secants, which would be angle JKL, that measurement will equal 1/2 of the difference of the two arcs caught between the two secants. And in this case, that would be the large arc, IM, around the far side, so then minus the arc, JL, around the near side. Okay, now why do we always take the large arc and subtract the smaller arc from it? Well, it's really very simple. We would like to have positive angle measurements. So we're going to subtract the larger value, okay, or take the larger value and then subtract from it the smaller value. If we did it in the opposite order, little number minus big number, we would end up with a negative angle measurement, and we do not know anything about negative angle measurements yet. Okay, so we always do big minus small. You should always get a positive number right there. Okay, so now we're going to take some time. We're going to look at some specific examples. Actually, there are 3, one to go with each of these situations. I will work a couple of them out for you, and then I'll leave the last one to you. Okay, so let's take a peek. Here we have a situation. Okay, what exactly is being shown in this problem? Okay, well, what type of structures do we have? Obviously, we have a circle. We have some line segments interacting with our circle. Okay, what type of line segments are these? They appear to be tangents. Okay, our tangents are only intersecting our circles one time each. Okay, and the rule is that the measure of the angle should equal 1/2 of the difference of the big arc minus the little arc. That's usually my shorthand notation for that, a big arc symbol minus a smaller arc symbol. Okay, so let's plug in the information where it goes based upon what we know. The measure of the angle. Okay, what is the measure of the angle from this problem? Well, the measure of the angle is x, so that will be the goal of the problem, to find out how big x is. Okay, that will equal 1/2 is part of the formula. He's built into it, so there he is. Okay, and that needs to multiply times the big arc. Do we know the measurement of the big arc coming around the far side of the circle? Yes, we do, 230 degrees. From that, the subtraction problem is built into the formula, so there it is. And from that, we're supposed to subtract the small arc caught between the two tangents. And in this case, we know that to be 130 degrees. So from here, we should work it out. We're going to work inside of the parentheses first. So x equals 1/2 times 230 degrees minus 130 degrees is 100. And obviously 1/2 of 100 is 50 degrees. There you go. Not too difficult. All right, let's look at another situation. Okay, different circle. We have some line segments interacting with our circle. Okay, what type of line segments do we have this time? This time it appears that we have a tangent hitting our circle once, and we have a secant which intersects our circle twice. Okay. Since the problem is giving us and asking us about arcs and angle measurements, we have a formula that talks to us about that, and the formula states the measure of the angle equals 1/2 of the difference of the big arc minus the little arc. So from the problem, let's plug in the information where it goes based upon what we know. The measure of the angle. Do we know the measure of the angle this time? Yes, we do. This time the angle is 20 degrees. So we plug it in. 1/2 is built into the formula. And from there, we have times the big arc. Okay, so let's look in the picture. Do we know the big arc caught between the tangent and the secant? Yes, this time we do, 160 degrees. And from that, we will subtract the smaller of the two arcs, which is y. Okay, so obviously y is the measurement that we are after in this case. Okay, so we need to get y isolated. Now, there's two different ways to think about this next step here, and it's completely up to you as to what you would like to do. Okay, what we have is our y is inside of our parentheses, so we cannot get to the y until the parentheses have been dealt with. Two ways to get rid of them, okay, but they both involve the same thing. 1/2 has to leave. Okay, so that 1/2 we can either obey the distributive property, and we can distribute the 1/2 to both the 160 and the y. But if you think forwardly a little bit, we are going to have to get that 1/2 off of that y at some point in time. So if we distribute it to the y, that's just another step that we're going to have to deal with later. So I would rather not distribute it. Okay, so let's see what we can do. Okay, instead of distributing the 1/2 to the y and the 160, I would rather just simply move it to the other side. Okay, so what is currently happening with 1/2? Okay, it is multiplying. So the opposite of multiplication would be division. But we know that dividing by fractions can actually be quite tricky. So here's what we're going to do instead. Okay, instead of dividing by a fraction, what you can do is you can multiply by the fraction's reciprocal. Okay, and whatever you do to one side, you have to do to the other as well. Now, why would you want to multiply times the fraction's reciprocal? Well, look what just happened. Our fraction has a 2 in the denominator. That is actually what's causing the problem, is the fact that there is a 2 in the denominator. How can we get rid of a 2 in a denominator? By introducing a 2 into a numerator. The 2 in the denominator will be canceled by the 2 in the numerator, and the 1/2 would be gone. Okay, so on the right side, we have a 2 in the numerator, and we also have a 20 in the numerator. 2 times 20 is 40 degrees. Okay, the 1/2 has been canceled by the 2/1 that we brought in, so the parentheses are no longer needed. The coefficient is gone, and that's what we wanted. Okay, we've got figured out a way to get the parentheses off of our y value so that we can now get to the problem. Okay, so now y is out of the parentheses. Okay, our next step should be that this 160 does not need to be there. How do you move 160 to the other side? Well, it's added. It's positive. So we would do the opposite of addition, subtract it. Okay, on the left side, 40 take away 160 is negative 120 degrees, which would be a little alarming at the moment because now we have a negative angle measurement, but we also have a negative y. Okay, we don't want negative y, we want positive y. How do you get rid of the positive or the negative off the y? We would divide by a negative sign. So if we divide the whole thing by a negative sign, it will change not only the sign of y, but also the sign of the 120 degrees. So y is 120 degrees from that problem. Now, they don't typically take that long to work. I just took a little bit of extra time to explain some of the math that was going on inside of that problem. Okay, there is one other situation, one other example. I would like you to copy this one down and give it a try. Okay, in this particular case, we have two secants that are originating from a common end point. If that's the case, then you have a formula that talks to us about the angles and the arcs. Please copy down the problem and see if you can get it worked out. I will expect to see the math that goes along with this one when you come to class on this day. I appreciate you getting the notes taken care of. I will see you in class.